This lesson is about polar bonds and nonpolar bonds. So you can think of a covalent bond as a little tug of war. So in a sense, we've got a covalent bond. We have electrons shared between two atoms. But if the electrons are shared evenly, like the picture on the left with the two hamsters, we would call that a nonpolar bond because each contributor is pulling with equal amount of force so that the electrons are evenly shared and essentially right in the middle of the two atoms in the bond. However, if you have a situation like the bottom right, where you have one side is much stronger than the other, well, you know what happens. The electrons are going to be pulled closer to one side than the other. So what happens is the electrons reside closer to atom B in this case than atom A, which causes a partial charge to be developing on atom A. So atom B becomes partially negative and atom A becomes partially positive. And again, it has to do with the fact that this tug of war between the two participants in the bond is not always even. And so that's what we call a polar bond. Here's another representation. Any atom that's bonded to itself is going to be a nonpolar bond because atoms, each atom has a characteristic amount of pull on the electrons. So the bond on the left with the two hydrogens is very even. They're pulling exactly evenly on those electrons and they're shared evenly. So there's no disparity between where those electrons reside. But on the right, we have chlorine on one side and hydrogen on the other. As it turns out, chlorine has a much stronger attraction to those electrons than hydrogen does. So those electrons, so in effect, chlorine's going to win the tug of war in this case. And the electrons are going to be closer to the chlorine than the hydrogen. So these are still considered covalent bonds. Those electrons are still shared between the chlorine and the hydrogen. It's just that they're not shared evenly. Chlorine is going to have more of that electron density around it than the hydrogen, and thus gives you a partially charged end of the bond, partial negative and partial positive. Now, this is called the electronegativity chart. The electronegativity is essentially a scale that ranks how hard the electrons can pull, each atom can pull electrons towards itself. And it's also color-coded, which is why I like this particular picture. So if you see the ones that are in red, like fluorine, have a high electronegativity. And what that means is that fluorine has a very strong attraction to electrons in a chemical bond. Whereas the yellow ones, the bright yellow ones, have the lowest electronegativity. And this is called a periodic trend because the electronegativity tends to go to be higher for elements that are high on the periodic table and for elements that are farther to the right on the periodic table. So you can think of fluorine as the highest electronegativity of any of the elements. And so the difference in electronegativity tells you whether you have a polar bond or not. And as I said before, if you have an atom bonded to itself, they have equal electronegativity, so it's a nonpolar bond. But if you have an atom that's bonded to a different type of atom, so for example, we have fluorine and oxygen, there's a difference in the electronegativity of those two elements, and so therefore the difference in electronegativity gives you a polar bond between those two atoms. Now, anytime we have a difference of electronegativity that's bigger than 0.4, we're going to consider that a polar bond. Now, what happens when you have a molecule that's made up of polar bonds? So here's a nice image of the water molecule. We have two hydrogens and one oxygen. And we know that structure very well. We've drawn it many times. Each hydrogen and oxygen bond, well, let's go back and look at the electronegativity. Oops, wrong direction. Hydrogen has an electronegativity of 2.2. And oxygen is 3.44. Well, if we take the difference of those two, that's well above 0.4. So the hydrogen-oxygen bond is a polar bond. And by the way, the element that has the higher electronegativity is the one that has the negative end of the bond, because that's the one that's pulling stronger. Okay, so let's go back to our water molecule. You can see here that we have two polar bonds in this molecule, so that the oxygen end of each bond is slightly negative, and the hydrogen end of each bond is slightly positive. So in effect, what happens is the entire water molecule becomes polar because it's made up of two polar bonds. And incidentally, they don't cancel each other out. So those two polar bonds give the water molecule a positive end on the hydrogen side of the molecule and a negative end on the oxygen side. And we know from the molecular geometry that water is bent. It's not linear. So therefore, those two polar bonds do not cancel out. Incidentally, it's this property of water, that it's a polar molecule, what is one of the reasons why water has so many special physical properties. Now, if we look at another example of a molecule, we have a classic example of a nonpolar molecule that has three polar bonds. Now, in this case, we have the molecule boron trifluoride. The boron-fluorine bond is a polar bond, but let's go back and look. So boron has an electronegativity of 2.04. Fluorine is 3.98. So if we take the difference of those two, it's well above 0.4. So that's going to be a polar bond. Interestingly enough, this whole molecule is completely symmetrical. The shape of this molecule, as you know from our molecular geometry, is trigonal planar. So what happens is, even though boron trifluoride has three polar bonds in the molecule, those three polar bonds are completely canceling each